Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston. It's actually a cold day here in Houston. It's like 40 degrees, I know, for Fahrenheit, what is that, like 6 Celsius. It's, that's what they call cold in Houston, by the way, which isn't that cold. Force of friction. So I rub my hands together, they warm up because of this thing called friction. Today we'll learn about what friction is. Houston, we don't have a problem because if you think about it, what's holding the apple to the board? Because gravity, right, is force going down, and why doesn't he just roll this way, right? We have the normal force, but there must be a force holding it, pushing back to keep it from accelerating. That's the force of friction. So what are the causes of friction? Friction's fascinating, actually. What it's understood is that there's like microscopic, like if you like to take the microscope or whatever and zoom in, there is these surfaces that aren't like 100% smooth. They might look smooth, but these microscopic little things like are like indentures. And then there's another picture right here of what friction might look like, is that they're like ridges that hold it together. So no surface is like 100% smooth, and that's what's going to cause friction to happen. Now, friction's a good thing. Right? If you're going around the corner in your car, then friction is going to hold you to the road instead of keep you going in the same direction that you're trying to go. If you go around the corner and there's ice, the friction is less, and you could go into the guardrail or worse. So friction's a good thing. All right? We don't live in a frictionless world. We live in one that isn't. So friction occurs when two surfaces are touching, and it's split into two categories. All right? There is what we call static friction, static. This happens when the object is not moving, like the case of the apple in just a minute. Now, let's think about this, right? What are some examples of that? A car on a hill. It doesn't move down the hill because of friction between the tires and the road. It's important, right? Or a box on a ramp, right? If it's not moving, right? Or honestly, if it's you pushing against a box that's standing on the floor and it doesn't move, what's holding it together is, right, you're applying a force in this direction and the box is applying a force backwards. That's the force of friction, isn't it? That's causing that to happen. You need to take the test. So just, it's in the stack somewhere over there. I'm making the next video here. So that's all right. You can keep going if you don't mind listening to me talk. The second one is friction occurs when two surfaces are touching and is split into two categories. All right, well, this is the same thing. What's the second category? Now, this is the one when it's actually moving. We call this kinetic friction, right? The word kinetic, for I-C-T, means to move. So some examples of this, all right, we just did one example a minute ago. Rubbing my hands together. Or what about, this example we had a minute ago where I am pushing on a box and it's actually moving. There's some acceleration. So as I push the box, at that point it's moving, and so that is now called kinetic friction. Or another one that's kind of a classic one. This is one, we don't do this very much in Houston, right, because of our weather. Somebody sledding down a hill. Now, they are accelerating down a hill, but there is a force of friction from the snow to the sled that's pushing back. It's not complete free fall. It is less friction. We can create situations where friction is less, and snow sledding would be one of them, but there is some friction. That's an important thing. So that's called kinetic friction. So what's the criteria for a frictional force? What's going to have to kind of work for this to happen? There is what we call, this is a fancy term, the coefficient of friction. Now, if you remember back to math class, coefficients are like, we say 3x. 3 is the coefficient. It's a number. It's a multiplier. All right? We use this when we choose to not ignore friction. Now, before now, we've ignored friction. Now we're going to pay attention to friction. Also, there needs to be a normal force between the two surfaces, which of course is, you need like all three of these things to happen. All right, this one, number one, if you will, number two, Number one, number two, number three, there's applied force trying to move that. You have to have some kind of a force applying to move that object. Like in the case of, let's go back. In the case of the box, that's the applied force by the guy. In this case, the force of gravity, it's actually this gravity, but actually when you solve it algebraically, right, it's the force, this force down here by gravity that's being applied based on the angle of the force. So if any of these are not met, you don't have friction. Okay? So that's the criteria for the force. And so I want you to imagine that you've got a couple of coins, right? And example number one is if I've got a coin and it's on a block of wood, right? This is wood. In the second case, it's like a long piece of wood. In the second case is I've got another coin and it's on a block of ice. All right? And if you apply a force to the coin, which one's going to go farther? I mean, you know this, right? It's going to go much further on the ice, accelerate more rapidly than it will on the wood. Because the surface of the wood versus the surface of the coin is more frictionful. Is that a word? And on the ice, it's less frictionful. I'm making up a word, by the way. And that's how that works. So how do we determine this coefficient of friction? We use the Greek symbol mu. All right, it's a little U with kind of a tail, and it's going to be equal to the force of friction divided by the normal force. That's it. And if you think about this, right, what are the units on the coefficient of friction if it's F of F divided by F of N, arrows and junk like that, right? That's a Newton, and that's divided by a Newton. What happens? The Newtons cancel. So we say that this is unitless. There are no units on the coefficient of friction. And it turns out that there's tables and tables and tables of coefficients of frictions. So if you've got two surfaces, surface A and surface B, so steel and copper, the coefficient of static friction, 0.53, kinetic friction, 0.36. Now, I want you to notice a few things about this table. Let's just think this through. What do you notice about the coefficient of static friction versus kinetic friction? Pause the video and think about it. You notice that in general, there's exceptions, that the static friction is harder or higher, if you will, than the kinetic friction. So it's more difficult to get something to start moving than to be moving it while it's already in motion. Does that make sense? The only exception we have here is concrete and rubber. The second thing I want you to notice is where do you see high numbers and where do you see low numbers? All right? So human synovial fluids, which is cartilage, right? Well, look at the coefficient of friction. Crazy, crazy small, all right? And this is even smaller. So it's almost frictionless. Or ice and steel, 0.1. But when you get a high number, right, steel and steel, it's a pretty high number, isn't it? All right? So if you will, the stickier the substance, the higher the coefficient of friction. Hopefully you're seeing that. So we can summarize that. Where do the numbers fall between, right? They fall basically between 0 and 1, some slight exceptions. So it's somewhere in the neighborhood of 0 and 1. And when do you expect a small value? I guess we've already said this, smooth surfaces, right? And these would be sticky surfaces, right? So 1's a big number and close to 0 is a small number. Next up, we're going to talk about how to do calculations with friction. We don't have no problems, Houston. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a